Okay, guys, so let's start. Okay, guys, so I want to complete this section, this chapter. We have just very few stuff remaining here. So I decoder, especially if you have into M decoder, I explained it before. For example, 2 to 4 decoder. You remember how it works? Yeah. So here the input here you have a binary number. As you see here, this is how it works. Okay. So the input can be a binary number from 0 until 3. For the output, if you have 2 inputs, I should have 4 outputs. For the output, only one output, listen to me, only one output is active, okay? And all the other ones are inactive, okay? Depending which number you have here. So this is number 0, number 1, number 2, number 3. So if if I have number 3, so number 3 is active in this case, because this one is active high, 1, and everyone else is 0. Make sense? If here is number 1, okay, which is 1, 0 this way, so actually output number 1 here is 1, and everyone else is inactive. This is decoder. I explained it. This decoder, for example, you call it 2 to 4 decoder in this case. Also, I explained here how can you add and enable. You know how to design it. You know the design using AND gates. Also, I explained is active low. Okay. Also, it's the same thing. I can make it bigger using 3 to 8 decoders. It's almost the same idea, same design. Also, I explained if you have 2 decoders, which are 2 to 4, each one is 2 to 4, how can you connect them together to create 3 to 8 decoder using inverter this way? Okay. I think this also I explained this one. Same things here. If you have 3 to 8, 2 decoder, each one of them is 3 to 8. I can combine them together to create a decoder that is 4 to 16. So here, if you look at this one as a block, so this one becomes 4 to 16 decoders. We have 4 inputs and we have 16 outputs. Okay. Yeah, and I think I don't remember 1 or 2 labs. You already used decoder in some labs. These are a chip. I explain how it works and so on. In this example, I explain using 2 to 4 decoders. So we have here 5 2 to 4 decoders. Okay, how can we create 4 to 16 decoders? So if you see this one, just one block, and the block this way, so this block becomes 4 to 16 decoders. So we have here 4 inputs, we have 16 outputs. Okay. So here, as you see, for the 16 at the output, we have 16. So I'm gonna get 4 from here, 4 from here, 4 from here, 4 from here. So total it becomes 16. Also, I need 1 decoder to enable so that only one here is enabled at a time. Okay. So if the number in this range, so I have to enable this one. Or if the number of the input in this range, so I have to enable this one. If it is in this range, so I have to enable this one. That's why I use another decoder here. Okay. The 4 to 16 decoder has an enable, and this is the enable of the selector. So this is like a selector decoder. I can use this enable here as enable for the 4 to 16 decoder. Again, that's what I do. So, but I did not explain this decoder, which is somehow also you used it in one lab. This decoder, you remember this chip when every time you use the 7 segment, you use this chip. So now I will show you how can you design this chip and why we need it. I would explain it in one lab, but I did for sure. I didn't explain the design. How can we design it? Okay. So if you have a 7 segment and you have already used 7 segment and you know how it works in one lab, okay. So if you have a BCD number and you know what I mean by BCD number, if you have a BCD number, which is number from 0 to 9, but this number is represented in 4-bit binary number, so from 000 until 1001, which is 9. Okay? So here the input here is the BCD number. The output here, it should be 7-segment code. 7-segment code. So what do you mean by 7-segment code? It means, as I have a table here, so I want to design a logic circuit that can do this conversion, okay? If the input is number 0, BCD, so the input here is actually BCD. The output here is 7-segment code. So what do you mean by 7-segment code? That's what I'm explaining now. If the input here is 0, okay? For the output here, I have segment A. You remember here, and we have segment A, B, C, D, E, F, G. Okay. So if the input is 0, 0, 0, which is number 0, so the corresponding segment code has to be 1 here, 1 here, 1 here, 1 here, 1 here, 1 here, in order to see number 0. And there should be 0 here. So turn this one off. That's what I mean by 7 segments. Same thing if it is, for example, number 7. In case of number 7, so I have to make sure this one here has to be 1. This output here, because this out, we have the output here, so I have to make sure there is a 1 here and 1 at B as well, 1 at C as well. Okay. Everything else is 0. Okay. That's why you use this chip. So this chip actually converts BCD code into 7-segment code, and usually we use it to display any number. If you have any binary number and you want to display it in the 7 segments, so you need to convert from this code to this code. You can see this table, and with these very nice figures here, if you have 0, 0, 0, so these are the ones I have. These are the output that they should be 1 on in order to see number 0. That's why you can see all of them on except D, 0. Same thing if you take any other number, for example, number 9. Here you can see here this is number 9. So this is the corresponding to code. You can see all the outputs should be 1s except E. This is E here. So E I have to turn it off. Okay. So if you look at number 8, this is number 8. Okay. Number 8, that means this is the corresponding code. So actually, for 8, the corresponding code is all of them are 1. Any question here? So again, I need a logic circuit. This logic circuit, this is the input, and this is the output. And this logic circuit is gonna actually, I will use it. Here, input here is a BCD number, and the output is the 7-segment. Okay, you already used this chip in several labs, but you don't know how we made the design, the internal design. You just use it. Okay, that's what I'm explaining now. So now, any question about the truth table here? This truth table. Okay. So now, once you have the truth table, can you design this circuit? Very trivial, very easy. So all what I can do here, this is like I need to make a key map for A. Okay, A should be function in ABCD. Then I have also to make a map for B, map for C, map for D, because each one of them should be a different circuit. And all these circuits have the same inputs, which is actually ABCD. Okay. So also keep in mind, because we have here we have four variable inputs. So we're gonna have 16 possible cases, as we see here in the maps. Okay. So this is the map of A. Is corresponding with this one here. But keep in mind, because numbers we should have numbers from 0 to 15. But because the input is BCD, so the input has to be until 9. So from 10 until 15, they should be they should be in the maps here. They should be don't care, because whatever the output with these inputs, I don't care if the output is 1 or 0, because they should not have. Okay? That's why you see here, I made these ones here don't care. Any from 10 to 15, because this input should not have. So if they have the input this one, I don't care what is the output. Okay? That's why here I voted don't care. Anyway, so as you see here, what I did for A, I made a key map, as you see here. Same thing for B, same thing for C, D, E, F, and G. Okay, and every one of them should have after simplification, they should be the function between the input A, B, C, D, and the output of this. Same thing, we have another one for B, C, D, and so on. Okay? And this is the circuit. This is how the chip you use. This is a chip used in one lab or a couple of labs. This is how this chip should look like. This is chip. Okay. So as you see here, we have this is the chip used, and this is chip. You have here input A, B, C, D, and then you have here output A, B, C, D connected to the shipping system. Any question? That's easy, right? Any questions? Good. The next thing I want to explain here in this chapter is actually encoder. We explain decoder. So always you can tell from the English name, decoder and encoder. It means this one has to do the opposite of decoder. Right? So what is decoder? As I just explained to you here, decoder, for example, if I have two inputs, I should have four outputs. This is a relation. Two, I should have four. Okay. Assuming I'm using all the possible cases for the input. Sometimes I don't use all possible cases. So if we are using all possible cases for the input, so if I have two, I should have here four. We have one output here. I'm going to call this is output 0, output 1, output 2, output 3. Okay. And this is the input, and this is the output. Always one of the output is active, and everyone else is inactive. As I explained, right? Depending on what number you have here. So if I have this number, which is number 2, so here number 2 has to be 1, and everyone else should be 0. Okay. This is decoder. Okay. So if we make an encoder, how it looks like, it's going to be exactly the same thing here, but I'm going to switch. This output, it becomes my input, and my input becomes my output. Okay. So actually, encoder is the device. Okay. This device should have, for example, if I talk about 4 to 2 encoder, it has to do the opposite of 2 to 4 decoder. Okay. So here, if I have 4 inputs, we have input number 0, input number 1, input number 2, input number 3, and then here I have a binary number. Okay? Everything we did here in decoder, I'm going to do it here, but in the opposite. Okay. So in the input here, in the input, only one input has to be active, and all other inputs should be inactive. Okay. For example, if I put here 1, I have to put 0 here. That's how it works. And based on which one is active, I should see the number corresponding number here. So if 3 is active, so I have to see number 3 in the opposite. Is that okay, guys? If this one is active, number 1, so I have to see here, number 1. It's the opposite of this one. So now how can we design it? Okay, that's what I'm going to explain here. How can we design it? It's very simple. Here, yeah, let's start with 4 to 2 encoder. So I have 4 inputs. As I told you, I have 2 outputs, as you see here. Okay? So the inputs, as you see here, this is the input. Let's make a truth table first. This is the input and the output. Okay. Is the, for example, here, if this one is 1, everyone else has to be 0. It's not allowed to have more than one here in the input. So if this one, everyone else should be 0. If this one is 1, everyone else should be 0. If this one is 1, everyone else should be 0, and so on. Okay? So if number 0 is 1, so the output here has to be number 0. If number 1 is 1, okay, so here number 1 has to, the output has to be number 1. If number 2 here, if Y2 is 1, so actually the output has to be number 2. If Y3 is 1, so the output here has to be number 3. Is that okay with the truth table? It's the same thing. It's exactly the same thing of decoder, but here I switch it. This one was input, now it becomes output. This one was input, now it's was output, now it's input. Okay. Now, how can we design? Okay, so we agree. Number 1, you should understand how encoder is different from decoder. It's just the opposite. Everything is the same, but the opposite. Okay. Number 2, you should understand how the truth table looks like. This is the truth table here. I don't have any other cases. It's impossible to have 1. It's impossible. Look at what I'm saying. Look how it is very easy. How can we design it? Okay, look here. for example, for E1. E1 has to be 1 here and 1 here. Okay. So 1 here, that means it has to be 1 when Y1 is 1. Has to be 1 when Y2, Y3 is 1. So if Y1 is 1, so E naught has to be 1. Or if Y3 is 1, E naught has to be 1. That's why this is how I'm going to make it. Very easy. So here E naught is equal to Y3 or Y1. If Y1 is 1 or Y3 is 1, E naught has to be 1. Same thing for E1 here. Look at E1 here. It has to be 1 here and 1 here. So here, E1 has to be 1 when Y2 is 1 or when Y3 is 1. That's why you can see here Y2 or Y3. You can notice something here. Okay, but what you are doing now is somehow different from maintenance. Some students. What I'm doing right now is different from what we did in midterms. In case of midterms, what we did, if this one is 1, so you have to say Y3 prime, remember, Y2, and then Y1 prime and Y naught prime. That's what we did before in similar, if you have a table like this one, okay? So, but I didn't do it this way here. You know why? Because in case of midterms, you have all possible cases for the input. Here, it's a special case. Here, when Y2 is 1, nothing else will be 1. It's for this one, it's just a unique case here. It's a unique record, okay? So here that means the way we do it here, somehow it's little different from what we usually do in case of midterms, okay? Because in midterms, in order to make this row a unique row, okay? The way we did it, we said Y naught, Y1 prime, Y2 prime, Y3 prime, in order to make sure this is for only for this row. Here, I don't need to do that because in this row is unique that Y naught is equal to 1 because it's not going to happen for any other row. Hopefully you understand it, okay? You don't be confused because this one is different. The input here is different from what we had before. The way you have to do it, guys, as I told you, you can see here, this one is 1 when Y1 is 1. This one is 1 when Y3 is 1. That's why you have to say here Y1 or Y3. If this one is 1 or this one is 1, listen to me. Okay, so this one is 1 or this one is 1, E0 has to be 1. Anyway, so here I just use here two OR gates as you see here. I can repeat the same thing again but for a bigger encoder, 8 to 3. It's exactly same thing here. We have 8 inputs, we have 3 outputs. Here, Y naught here is 1, only in this case, it shouldn't be 1 anymore. Y1 only in one case here because it's not allowed to have more than 1 input with 1. It's not allowed, okay? But anyway, so you can see here. So now, if Y1 is 1, the output has to be number 0. If Y4 is 1, the output has to be number 4. If Y6 is 1, the output has to be number 6, and so on. Same thing as I did before, but this is like a bigger size. Any question here? Okay. Now, how can we design this encoder? Because in final exam, okay, if I ask here a question here, I will ask you to design. For example, I can ask you to design a 8 to 3 encoder. So in this case, you have to make the table. You have to show me the equations here, and you can show me this block diagram, and you need to draw the circuit as well. Okay. So here, I'm not asking you to memorize anything. If you just understand it, it will be very easy. Okay? Number 1, you should be able to do, if you understand how encoders work, you should be able to do the truth table. That's number 1. Number 2, in order to get this equation, it's very trivial, very easy, much easier even than midterms before. For example, if I want to design E naught, input here. We have one here, and we have one here, and we have one here, and we have one here. This one happens at here, y1. This one happens here at y3. This one happens here at y5. This one is actually y6. So that means A node 1, if y1 is selected, 1 over y1 over y5 is 1, y6 is 1. And this is exactly what I do. Okay. Let's have another one. For example, if E2. So same thing, E2. We have one here, one here, one here, one here. So E2 has to be 1 when Y4 or Y5 or Y6 or Y7. That's okay? That's it? Any question? Okay. So now you should understand what is encoder, how it works. Okay. You should understand how can you design it. As I told you guys, the purpose of this course is not building a microcomputer system or any digital system. The purpose of this course just to teach you some devices that get in your coming courses. You will learn how to. No one will explain anymore what is code or how can you design it. No one will explain how can you or decoder or multiplexer or anything. Okay. Any questions? Let me tell you here, the last thing we have here, what we call a priority encoder. Okay, I want to make, this is, okay, this one is encoder, I think it's okay, but but this one has two problems. I want to address these two problems, okay, in this design here. The first problem is, what if, for example here, what if the user, for the input, only one input has to be 1 and everyone is 2. Right? What if you make more than one input is 1? Okay? For example, if I make y3 is 1 and y6 is 1, just here, okay. If I put here 3 is 1 and 6 is 1, okay. So based on, if you look at the equation here, 6 is here. So actually, A node is 1, E1 is here, okay. So E1 should be 1, 3 is here, should be 1. That means I'm gonna get number 7. Okay, so if you make here, because if you want to use this design correctly, it's not allowed to make more than one input 1. But if you do, for example, here the input is 3 and the input is 6, I'm gonna get something random. It's not 3, it's not 6. Okay, I get something different. Now I will come to the idea of priority. What do you mean by priority? It means, look here, guys. For example, if my priority is this way, so 7 has more priority than 6, has more priority than 5, has more priority than 4, and so on. You can design it the other way if you want, but I want to make a priority. So priority means I want to change this design to that here I have 2 inputs. Is that okay? But one of them has more priority than the other one. So the output here has to be 6. You got what I'm saying? So if you have here, if one here in 7, but 7 has the highest priority. So regardless what you put here, I will get 7 because 7 has higher priority. Okay? If I have here, if you put 2 ones, 1 at 3 and 1 at 1, so I will get 3. So only the output will be even if the input, even if you have 2 inputs or more than 2 inputs, have 1, okay, the output will be similar to the active input that has higher priority. That I will have okay. This is one problem I want to solve. The second problem I want to solve is if all inputs are 0, here I will get number 0. It is the same thing if y1 is 0 and everything else is 0. So how I can differentiate between these two cases? This is the second problem we have in this design. If these are not a problem for you, just okay, you can just use this circuit. It's totally fine. What I'm saying? So here, what I'm saying, this circuit, if all inputs is 0, which is for sure, it's not allowed case. But if it happens, the output will be 0 with 2. When y, I think we should have here we have y0, but here in this design we don't have, we don't need it, but that's okay. So here it's the same thing. If you have y0 here is 1. So how can I differentiate between that? Okay, that's what we call a priority encoder. The purpose of the priority encoder is to fix these two problems. That again, there is a problem when all inputs are zeros. Okay, I should not get zero. Or I have to differentiate. Okay. If input number 0 is active, or if all inputs are zero. That's why to solve this problem, I'm going to add one more input here. For example, here we have in this priority encoder, I have 4 inputs and I have 2 outputs, right? This is a relation. If you have 4 inputs, you should have 2 outputs. But I will add another input here. This input will tell me if all inputs are zeros or not. Okay. So here, yeah. So as you see here, guys, I'm going to add one more output here, one more output. If this output is 0, that means all inputs are zeros. Okay. But if you have in the inputs, if you have some inputs are selected, so in this case here the output will be 1. Okay. Again, you guys, my problem is that when all inputs are zeros, I will get the same output. If input number 0 is active and other inputs are inactive. In both cases, I will get number 0 at 0. I want to differentiate. To do that, I'm going to have here one output here, as you see. This output will give me 0, just in case when all inputs are zeros, otherwise will give me 1. Okay, this number 1. Number 2, also I want to solve the priority issue I told you about. That's why I'm going to change the table. Look how I made this table here, guys. Here I'm assuming, again, this is a design, you can design it the way you like. So here I want to give more priority to number 3. So this one has highest priority, this one has the lowest priority. So the way I will design it, as you see here, guys, if I have here 1, if this one is 1, regardless what you have here, it doesn't matter, the output has been number 3, because number 3 has the highest priority. So even if you have 1, 1, 1, 1, 1, still I will get 3. So no matter, it doesn't matter what you have here. If this one is 1, because this one has the highest priority. Okay? We have another case. If this one is 0, but this one is 1. So it doesn't matter what you have here, because T3, T2 has more higher priority than T0 and T1. So in this case, I will get number 2. Okay. If I go up, if this one is 0, this one is 0, and then here I have 1 in G1. So it doesn't matter what you have here in G0, it doesn't matter what it is, because even if you have here 1, it doesn't matter, still the output is 1. Because 1 has more priority than G0. Okay? And then after that here you have here 0, 0, 0, 1 has to be number 0. Okay, guys, any question? So again here I solved 2 problems. The first problem I introduced the idea of priority. If number 3 has higher priority, so regardless what you have here, okay, I will get number 3. Okay. Now, okay, how I can design the circuit now? Okay, look how I made it. Now I have these inputs. We have 4 inputs. I have 16 cases. These are the 16 cases we have. Okay, so in this case here, 0, 0, 0. This is V has to be 0, and this is the case here, 0, 0, 0, 0. V has to be 0. Okay. In this case, 1, 1, 0, 0, 0. So I have to get this output here. Okay, which is this is the case here. Okay. And then after that, this case here actually is going to be 2 cases here in this table here. 1 case here and 1 case here. 1 case when X is 0 and 1 case when X is 1. 2 cases. And in the 2 cases, I'm going to have the same output. In the 2 cases. Makes sense? Here, but this one here is going to be 4 cases, because we have 4 different cases for this one. That's why you can see this one here, and then here, and then here, and then 4 cases. And in the 4 cases, I will get the same output. Okay? Last one here, this one is going to be actually 8 cases. You have to put all possible cases for this one. Okay, as you see it, look at the color. That's why I use different colors. And in all of them actually, all of them, you have the same output, which is this. Okay. Again, once you have this table, it's very easy after that to use maps to design it. Okay. Anyway, because we need to start the test now. Okay. I will try to review it. Let's see.